Hello students. So the purpose of this recording, which is part 2 of the bit on using logarithms to do algebra, is going to involve using logarithms to solve motivated exponential equations. So the first application that I think I want to think about has to do with radioactive decay. So here's the setup. So if you have a radioactive substance, it decays at a rate proportional to the amount of that material present. The more of uranium-232 there is, the more of it will decay at any given moment. So that's exactly what it means to be an exponential function. Exponential functions are functions whose quantities change at a rate proportional to how much there is. So radioactive decay is modeled by an exponential function. So let's keep on reading. So scientists often find it convenient to record just the half-life of a radioactive substance. Lambdas are not uncommon letter to be used for it. Not that there's anything magical about what letter you use to denote a constant. So the half-life is the amount of time needed for half of the amount of material present to decay. If a radioactive material has half-life lambda, and you start with some initial quantity q0, then I claim that after some amount of time t, the remaining quantity is given by the initial quantity, and then just figure out how many times you need to divide by 2. And that turns out to be 2 to the negative t over lambda. So maybe I'll motivate that statement a little bit to the side. So let's suppose you start with some initial quantity, q0, and you know that the half-life is given by lambda. Then that means every time lambda time passes, the amount present will be divided by 2. So to determine the quantity at some time t, here's all you need to think about. Just think about how many times must I divide by 2. So every time lambda time passes, you have to divide by 2. So you just need to figure out how many half-lives have passed. So how many times must you divide by 2? That's the same as asking how many half-lives have passed. Well, that's easy. You just need to know how many times the half-life goes into the amount of time you've waited. That's exactly t divided by lambda. So you need to divide by 2 t divided by lambda times. So you want q0, start with q0, and then you divide by 2 to the number of half-lives that have passed. And that's all it is. That's exactly what this formula says. The end quantity, and this is a formula that's worth remembering, the final quantity after you wait some amount of time is given by the initial quantity times 2 to the negative amount of time you've waited divided by lambda. Let's just do an example. So U-232 has a half-life of 70 years, approximately. How long will it take 1 kilogram of U-232 to decay down to 1 gram? So let's set all this up. So you're told you start with 1 kilogram. So how long will it take for 1 kilogram to get down to 1 gram? So you start with 1 kilogram, you want to eventually get down to 1 gram. There's Q0 to decay down to 1 gram. So there's the final, there's what the eventual quantity will be. And you know the half-life is 70 years. So this is telling you the half-life. And you want to know how long it will take. So it looks like you want to solve for the amount of time that's passed. So let's just use all that. So apparently we want to solve for t, and let's write down the equation. So the end quantity is 1 gram equals 1 kilogram times 2 to the negative. T is the unknown that I would like to solve for, divided by 70 years. Cool, so there's the thing that we need to solve. I guess it's useful to get all of the masses into the same units, so I'll leave the 1 gram alone. 1 kilogram is 1,000 grams equals, times 2 to the negative t divided by 70 years. So there's the equation that I need to solve. It's going to be an easy equation to solve. Let's start by, so philosophically, what should you think when you want to solve an equation? More than one way to think about it, but one way to think is think of the complicated side as being some instructions that start with t, and you want to undo all of those instructions. So you start with t. The first thing you do is you multiply it by -1 and divide by 70. All that is in the exponent of a 2. So take t, make it negative, divide by 70, put it in the exponent of 2. Then take the result of that and multiply it by 1,000 grams. The last thing that happens is you multiply it by 1,000 grams, so the first thing you should do is undo that. So let's do that. So I see 1 gram divided by 1,000 grams is equal to 2 to the negative t divided by 70 years. So now this, one thing can happen first. The grams cancel, right? So now I see an equation that is in logarithmic form. Nope, it's in exponential form. And the stuff that I want to find is in the exponent. So I should rewrite this in logarithmic form. So I'll see log base 2 of 1 over 1,000 is equal to negative t over 70. Now it looks like I've put myself into a bad situation by using all the space to the right. So I'll free myself up some space. You've already written this down anyhow. Alright, so I see what I have to do if I want to get t on its own. Looks like I just need to multiply by -70. Yeah, so maybe I'll do that. Let's multiply by -70. So I'll wind up with t equals years. I was so good about leaving the units in, but then I erased them at that step. So t is equal to -70 times the log base 2 of 1 over 1,000 years. And so you might look at this and object. So this is saying that's how long you have to wait for 1 kilogram to decay down to just 1 gram. And this looks negative, doesn't it? it's got a negative sign right here. So that, on the one hand, should make you upset, but there's another thing that you should notice, and that's, look at this quantity. We can simplify that a little bit. That's a fraction. That's 1 over 1,000. I can rewrite that 1 over 1,000 as 1,000 to the power negative 1. So let's actually do that. I'm going to include some steps that maybe you wouldn't in most write-ups. I see an exponent here. I can pull that exponent out. That'll give me, well, negative 70 times negative log base 2 of 1,000 years. Those two cancel, leaving me with 70 times the log base 2 of 1,000 years. And this is an application question, so I kind of care about how big that quantity is. And I can simplify log base 2 of 1,000 a little bit by using the fact that 1,000 has some 2's in it. But instead of doing that, let's actually just make the computation. Let's have a computer help us. All right, here we go. I'm going to pause it, and I'll be right back. All right, there we go. Computation has just happened. And there's the result. The log base 2 of 1,000 times 70 is approximately 697. So, this quantity is approximately 600, maybe I should round correctly, 698 years. So if you start with 1 kilogram of uranium-232, you want to know how long it'll take for that uranium to get down to 1 gram. You've got almost 700 years to wait. That makes sense? Well, I don't know why I'm waiting for you to respond. Nice. So there's one application. One other application that's built on top of the idea of radioactive decay is carbon dating. There's one quantity in the atmosphere that, well, there's one radioactive element that is present in the atmosphere regularly that has a long enough half-life to allow for computing how long various things have been dead. So let's talk about that. So here's the setup. The interaction of solar radiation in the atmosphere produces a radioactive isotope of carbon, namely carbon-14. As a consequence, the proportion of carbon-14 in the atmosphere stays about constant. And if you're a living animal that keeps on breathing air in and out, then the amount of carbon-14 is staying about constant in your body. You keep on taking new carbon in from the atmosphere and exhaling. On the other hand, once you die, you stop taking in new carbon-14. So the new carbon-14 stays in the atmosphere, it doesn't go into you. And so the carbon-14 in your body decays exponentially. If we know the half-life of carbon-14, which we do, it's approximately 5,500 years. And as a reminder, half-life is often denoted lambda. So an archaeologist can use the quantity of carbon-14 in an animal to determine how old that animal's remains are. Okay, cool. So let's do that. Suppose that by using the mass of the animal and knowledge that while it was alive, the concentration of carbon-14 should be constant, you find that when the animal died, it should have had 4 grams of carbon-14. So that's the initial quantity, Q0. You observe that when you dig up the animal and measure it, it has 0.1 gram of carbon-14. how long dead is it? That is, I want to know how much time has passed? You just need to solve for t. So let's just take those known values and solve the equation. So there's right here is the equation that models radioactive decay. The amount that's in the animal when you dig it up, that's Q of t, that's the quantity at the time now, is 0.01 grams. 0.01 grams is equal to Q of t. That's the same as Q0 times 2 to the negative. Well, there's a goof there. I'll correct it in the version before it goes online. Q0 times 2 to the negative t over lambda. So that will be, let's just write everything out, 4 grams times 2 to the negative, I would like to solve for t, divided by lambda. Nice, so there's a thing to solve. I need to solve this is equal to that for t. So let's go ahead and get started. So I guess the first thing to notice is the units are all consistent. So I can divide both sides by g in order to cancel the grams. I guess I should also divide the 4 over to the other side. So that will give me 0.01 divided by 4, which I could simplify, is equal to 2 to the negative t divided by lambda. And I'll suppress all of the units. I'll need to remember that time should be measured in years. So, well, I guess let's simplify that left-hand side. I know what 1 divided by 4 is. 1/4 is 0.25, so this quantity should be 0.0025. All right, so I know what I need to do. I'll take the log base 2 of, I'll rewrite this in logarithmic form. That's the same as taking the log base 2 of both sides. Wind up with log 2 of 0.0025 is equal to negative t divided by 5,500. And I should say, those numbers that I'm using for the half-life are approximate. You can find much more precise estimates of the half-life by looking online. And those numbers come from experimental evidence. Excuse me, taking a sip of tea. So, I know what I need to do to solve for t. It looks like I need to multiply by negative 5,500. So I'll get negative 5,500 times the log base 2 of 0.0025. And again, I see this negative sign, which maybe makes you upset. It at least should make you nervous. But I also see this quantity in here. Well, that's definitely less than 1. So the log base 2 of all of that should be less than the log base 2 of 1, which is 0. So that means all of this is negative. So I see a negative times a negative is positive. So that should convince me that this is actually okay. This whole thing is in fact positive. All right, but again, if you were to say someone asked you to compute the amount of time that passed and you told them that it was 5,500 times the log base 2 of 0.0025, they would say, okay, great. What is that about? Because they probably care about, is it like 1,000 years old, 10,000 years old? That's what they're asking you. So let's get that decimal approximation and see what it is. So I'm going to give myself some more space vertically. You didn't need to know that. I'll be back with the computation. All right, we are back. So there's the thing I wanted to compute, negative 5,500 times the log base 2 of 0.0025. And apparently, that is approximately 48,000 years. So let's just write the summary. We solve for t. That t is how long ago the animal died. This animal died 48,000, approximately 48,000 years ago. So that's the handy thing. You can take a measurement in the now, and in fact, the quantities that you measured were this 4-gram number and this 0.01 gram number. Those are both perfectly reasonable measurements to get, and you can get a conclusion that is actually a pretty big number. Nice. So that ends the applied portion of this lecture. I have two more equations I would like to solve. Let's go ahead and solve them. So let's solve this equation. 7 times 2 to the x is equal to pi times 3 to the power x plus 1. Now, when you see just an equation written down, you shouldn't assume that it'll be easy to solve. Many equations can't be solved by algebraic means. You can get estimates for what the solution should be, and even intuition about how many solutions there should be, by doing things like looking at graphs. Which, you know what, let's go ahead and do that. I'll pull up a graph. We can estimate how many equations it looks like there should be. Okay, we are back. So I asked it to plot 7 times 2 raised to the x and pi times 3 raised to the power x plus 1. Notice the parentheses. Those are important. You need to remember order of operations. Parentheses, exponentiation, multiplication, division, addition, subtraction. So if you need to you need to evaluate that x plus 1 before you exponentiate, which you do, you need it to be in parentheses. Happily, things like Wolfram Alpha give you pretty print, so you can read this and decide if that's actually what you wanted to plot. It is. There it is. It looks like there's a solution somewhere in this range. So let's go ahead and zoom in on where that solution seems to be. So let's plot this. Let's restrict the domain. All right. And we're back. So now we see where the solution should be. And by looking at the big scale graph, we saw that it looks like there should only be one solution. There it is. I won't play the whole zoom in game, but it looks like it's somewhere between negative 0.5 and negative 1. All right, so that's progress anyway. I'm going to take this and move it to the side. We'll maybe play with that same graph later. So let's try to solve this, and I gave a comment here about a technique to try. So let's apply a log to both sides. I claim that any old log will walk, so maybe I'll even not specify a base. If you have a favorite log, use that. If you think applying log base 2 will be good, do that. So let's write this down. So applying a logarithm to both sides, I'll get log, I won't even specify the base, 7 times 2 to the x is equal to log of pi times 3 raised to the x plus 1. And that might seem like it's just made everything worse, but I can take advantage of logarithm laws. I see multiplication inside of those logs. That'll become addition. Log 7 plus log of 2 to the x equals log of pi times log, plus log of 3 raised to the x plus 1. I see exponentials inside of those logarithms. So here's the thing to notice now. This is a linear equation. And let's just go ahead and check. So I see log of 7. Well, that's a complicated number, but it's a constant. I see x to the power 1 times the log of 2, so that's x times a constant, plus a constant, plus x plus 1 times a constant. So I can solve this as a linear equation. I just need to accept the fact that the constants look complicated. So what's the algorithm to solve a linear equation? Get all the x's to the same side by doing some subtraction. Get everything that's not an x to the other side by doing some subtraction. And then divide by whatever's next to the x. So I can do that. So let's see, I guess this I'll subtract to the other side. So that'll give me x times the log of 2 on the left-hand side. I've subtracted, well, no, I'll write it at the back end. So I'll remember that I need to put that log of 7 back in. No, I'll just put it back in now. So I've subtracted the log of 7 to the other side. There was already on the right-hand side the log of pi. And maybe I'll distribute the log of 3 over the x plus 1. So log of 3 times x, log of 3 times x plus log of 3 times 1. All right, so I see a piece right here that has an x. I'll move that to the other side. So I'll see x times log of 2 minus x times log of 3 is equal to log pi plus log 3 minus log 7. And I need to buy myself some more space, so I'm going to, those of you walking along with me, somehow it matters a little bit less now that I have bad space management, because you can go ahead and pause this video and find yourself another piece of paper. So let's try to solve that equation. So it looks like on this side I should factor out the x and do some division. And while I do that, maybe I'll also look at this side and say, well, I can write all of those as a single log using logarithm laws. So on the right-hand side, I'll have x times log 2 minus log 3 with parentheses. Those parentheses are important. Equals, and all the stuff on the left, well, I see log pi plus log 3. That addition will turn into multiplication, minus log of 7. That subtraction will turn into division. Log of three times pi all over 7. 3 times pi divided by 7. So it looks like all the stuff next to the x needs to be divided over to the other side, so I'll end up with x equal to log of 3 times pi all over 7 divided by, well, look at what's this quantity is. Maybe, like, this quantity is what I'm going to divide by. So maybe I can do some simplification while I do this. So log of 2 minus log of 3, that's the log of 2 over 3. So one thing that you could notice now to simplify just a bit, there's not much simplification you can do, is I see a log divided by a log. That's exactly what you see on the right-hand side of the change of basis formula. So it looks like here is the thing that's going to become a new base. And that's why I didn't bother choosing a base, because I knew I would do something like this. So this is the log base 2/3 of 3 times pi all over 7. If you wanted to simplify, that's maybe the farthest I can see about simplifying. So let's go ahead and check that this agrees with our intuition. So let's bring this back, and you don't need to see what I'm about to type. Rather, you don't need to see me typing what I'm about to type. So there's what I entered in, log base 2/3 of 3 pi over 7. Here it is in pretty print. That agrees with what I wanted. Log in the base 2/3, 3 times pi over 7. Okay, yeah, that's the same as this. There is the other format that it was written in. That's apparently somewhere around negative 0.7. Which, yeah, that agrees. We said it was somewhere between -1 and -0.5. That's somewhere between those two numbers. Groovy. So let's go on to think about the next one. Here's an equation to be solved. 4 to the x plus 2 to the x minus 1 is equal to 0. So we've seen this type of trick used before, where you see something that looks like a complicated equation, but really it's just like a quadratic equation evaluated at some other function. And this is exactly that situation. So let's see how to do that, how to realize that. So let's write it out again. So I want to solve 4 to the x plus 2 to the x minus 1 equals 0. Well, check it out. 4 to the x is just the square of 2 to the x. In order to check that, if you don't believe me, let's take 2 to the x and square it and see what we get. So that's exactly the same thing as 2 to the x times 2, which is the same thing as 2 to the 2 times x, is the same as 2 to the 2 to the x is 4 to the x. So whenever you see two different exponentials and it looks like their bases might be pretty closely related, see how their bases are related and use that. Because if we take advantage of that, so that means I can replace 4 to the x, I can replace this bit, with 2 to the x to the power 2, this bit. So let's do exactly that, and I'll even add a little bit of color coding to help. So I see 2 to the x squared, because there's 4 to the x, sorry, I want that squared to be black, plus 2 to the x minus 1 equals 0. And I've done that color coding because it suggests a substitution. Let's make a substitution. Let's substitute y equals 2 to the x. So all I'm doing is I'm renaming 2 to the x. I'm giving a variable that job. Because if I make the substitution, the equation becomes easier. It becomes y squared plus y minus 1 equals 0. That's now easy to solve for y. I can use the quadratic formula, I guess. And if I do that, I'll get y equal to negative b plus or minus the square root of b squared minus 4 times a, 1, times c, negative 1, all over 2a. Simplify that a little bit. Right. Double negative becomes positive. In the square root, I see 1 plus 4, so that's 5. So I see negative 1 plus or minus square root 5 over 2. And this might look like I'm done. I certainly have solved for a variable, but did I want to solve for y? No, x was the original variable. But this gives me two different equations that I now need to solve. Y is 2 to the x, so I have two different equations to solve. I need to solve 2 to the x is equal to negative 1 plus square root of 5 all over 2. And I need to solve 2 to the x is equal to negative 1 minus the square root of 5 all over 2. All right, well, those are both exponential equations. I could just rewrite them in log form, but first let's decide if they're even reasonable things to say. Remember, an exponential can only ever be positive. 2 to the x can't be negative and it can't be 0. Oh, that's not what I wanted to do. So this quantity, negative 1 plus the square root of 5 over 2, let's decide if it's positive or negative. So the square root of 5 is 2 and some change, so I see negative 1 plus a little bit bigger than 2. Okay, so that's a little bit bigger than 1. Divide by 2. Yeah, that's positive. So that means I can rewrite this in log form as x equal to the log base 2 of negative 1 plus root 5 all over 2. That doesn't simplify in any helpful way. Then let's look at this side. So I see negative minus some stuff, so that the numerator is just negative. Divide by 2 is still negative. This is a negative number. So this exponential must be positive, has no solutions. So this is the only solution to this equation. And because this wasn't an application-driven question, I'm not going to bother getting a decimal approximation. I don't know why the person who's interested in this, the number is interested in it, so I'll give them the exact value. It's that. Let's do a similar one. So, all right, while this in class, I would have done one of these and had you do the other, and that would be like the exit quiz. Once you got the answer, you would be allowed to leave. But I can't do that here instead, so I'll talk through it. So it's going to be a similar substitution, and in fact I suggest the substitution. Let's substitute y equals 3 to the x. And that's a good idea because in looking at this, I see a 3 to the x right there. I see a 3 to the x right here, so I can replace that with a y. Let's look at this 9 to the x, though. Well, 9 is just 3 squared. So that means 9 to the x, that's just 3 to the x squared. So under the substitution, that'll become y squared. So this whole equation will become y squared plus 2y minus 4 equals 0. And this one, I mean, solve it the way you want to solve it. You probably already solved it, and you're just watching this to make sure that you get answers that agree with what I get. I'll use the completing the square technique. So I'll see y plus, that's a 2, so I know the thing next term should be a 1 squared, because if I expand this out, I'll get y squared plus y, so plus 2y, good, plus 1. So I need to subtract that 1, minus 4 equals 0. Oh, okay, well that's easy to walk with now. Y plus 1 squared equals 5. Y plus 1 equals plus or minus the square root of 5. Y equals negative 1 plus or minus the square root of 5. But again, I wasn't interested in y. Y was a fake variable that I added to make the algebra easier. I forgot about the 3 to the x because I could do the algebra without the 3 to the x there. Now I have to put the 3 to the x back. So I'll get two equations. Hello, cat. 3 to the x is equal to negative 1 plus square root 5. And I'll get 3 to the x is equal to negative 1 minus square root 5. Just like before, that quantity is negative. This quantity, square root of 5, is like 2 and some change, so this quantity is positive. So this first one has solution x equal to the log base 3 of negative 1 plus the square root 5. The second bit is an exponential equal to a negative. It has no solutions. So this is the only solution to that equation. Wonderful. Well, I'll go ahead and post this. I'll talk to you when I talk to you.